Welcome to today's lesson on rotating a matrix clockwise by 90 degrees in JavaScript. In this video, we'll walk through the problem, understand how matrix rotation works, write code to solve it step by step, and then discuss time complexity. Before we dive into matrix rotation, let's first clarify what a matrix actually is. In its simplest terms, a matrix is an array of arrays. Here's an example of a 3x3 matrix in JavaScript. We define it as an array where each element is, in fact, another array. As you can see, this outer array, right here, contains 3 inner arrays, 1, 2, 3, and each of these is representing a row within the matrix. In this case, the matrix holds numbers 1 through 9, structured as 3 rows of 3 numbers each. Let's expand on this idea. A matrix can also be described as an array within m nested arrays of length n. In other words, we have m number of rows and n number of columns. This is just a general way of defining any matrix. In our example, we can see that m, the number of rows, is 3, and n, the number of columns, is also 3. So this particular matrix has a size of 3 by 3. Each row and column together are creating this grid structure of the matrix. Now that we know what a matrix is, let's take a look at how we label its individual elements using indices. Each element in the matrix can be defined by 2 numbers, a row index and a column index. The row indices are represented by I, which corresponds to the rows in the matrix. In this case, I ranges from 0 to 2, and that's because we have 3 rows. Over here, J represents our columns, and again, our indices range from 0 all the way up to 2. So when we refer to an element in the matrix, we use a combination of the row and column indices. For example, the number 1 is located at position 0, 0, which means it's in the first row, I equals 0, and it's in the first column, j equals 0. Whereas the number 5 is going to be in the position 1, 1. It's in the second row of I equals 1, and the second column of j equals 1. The problem we're trying to solve today is writing a function that rotates a matrix 90 degrees clockwise. As you can see, we start with this square just to visually represent how things rotate. It's divided into 4 distinct colored quadrants, and our goal is to rotate that square 90 degrees clockwise. So watch as each quadrant shifts into its new position. You'll notice that this top left teal green color, this quadrant, rotates from the top left now to the top right. The top right quadrant, that's blue, now is the bottom right quadrant. The bottom right purple quadrant is now in the left position, and this bottom left burgundy quadrant rotates up to the top left. This is a simple visual of what we mean by rotating an object 90 degrees clockwise. Now let's apply this concept to a matrix of numbers. Here we have the same 3x3 matrix of numbers 1 through 9 that we referenced earlier. And our task is going to be rotating this matrix 90 degrees, just like we did the square. First, let's focus on the top row, 1, 2, 3. In the rotated matrix, this now becomes the last column. 1, 2, 3 are now vertically aligned on the right. Now let's move on to the second row, numbers 4, 5, and 6. Again, after the rotation, these numbers become the new middle column. Still in the same order, 4, 5, 6, but now they're vertical. And finally, if we highlight that bottom row of 7, 8, 9, that's going to move into the first column. And just like before, that row is now vertically aligned in the first column. This demonstrates how rotating a matrix 90 degrees clockwise is actually transforming rows into columns but still keeping the order of the elements the same. Before we get into the numbers, let's quickly look at how the positions of the elements are changing. As I mentioned before, in any matrix, we're going to have two indices to identify the position of each element. In this original matrix, each element is identified by I, J, where I is the rows and J is the columns. On the rotated matrix, the elements are now defined by J as the rows, and I is now representing the columns, but the actual element location will be defined by this formula that we'll discuss later, which is m minus 1 minus I. The main thing to focus on for this slide is that I becomes the new column index and J now represents the rows. So these have essentially flipped on the axis from where they were before. Let's start by discussing a pattern we observe in this rotated matrix, which is that J originally is the column index and it becomes the row index in the rotated matrix. Let's visualize what that will look like. Here we have the indices of the top row, numbers 1, 2, and 3 in the original matrix. In the original matrix, where we have I representing the rows and J representing columns, the number 1 is in position 0, 0. The number 2 is in position 0, 1. And the number 3 is in position 0, 2. Now on the rotated matrix, where I becomes columns and J now represents rows, we see their new position moves. So number 1 is now in position 0, 2. 2 is in position 1, 2. And number 3 is in position 2, 2. You can see that right here. You can see here that the J that used to represent columns now represents rows. So those numbers are the same. The same is true for the next row, 4, 5, 6. The J index flips from the original to the rotated, and those numbers remain the same. And the same thing is here for the numbers 7, 8, 9 in the final row. That also becomes a column, and the J index location remains the same. So the key pattern here that we want to notice is the column indices in the original matrix are now becoming the row indices in the rotated matrix. This means they map directly from the original matrix into the rotated matrix. Now let's shift our attention to the other index, index I, that starts in the row position for the original matrix. And when it's rotated, it moves over to the column area and is now represented numerically as m minus 1 minus I. Let's go back to our visual here and see what patterns we can observe. So again, we're focusing here on the transformation of I, which in the original matrix starts out as the row index, and when it flips, it becomes the column index. There's a couple observations we see here. Row 1, which is in index 0, is flipping to be a column, and now all of these numbers are in index 2. So they've reversed. They used to be in 0, now they're in 2. Now you have row 2, 4, 5, and 6 in index 1. When you flip that, it stays in index 1 because it's right in the middle. And last, we have the final row, row 3, 7, 8, 9. That is in the last index, index 2, and when that flips into a column, it is now in index 0. So if we look specifically at the first and last, you can see that they have reversed order. Row 1 in index 0 is now in the last index 2. Similarly, row 3, the final row in index 2, is now in 0. So we see that there's an inverse happening when they transform into columns. Let's see that represented in the element positioning. So we have all of I in 0 in the original matrix, and they now move to 2s in the final matrix. For 4, 5, and 6, they start in position 1 for I, and they end in position 1 in columns. And for 7, 8, 9, they start in position 2, index 2 for I, and are transposed from the last to the first index when rotated. Now that we understand that the I index flips when it turns to columns, let's revisit that formula we discussed. So the formula is m minus 1 minus I being that original row index. That will equate to the new I column index. The formula is pulling information from the original matrix. So when we see m here, we're referring to the number of rows, which is 1, 2, 3. When you look at m minus 1, that's referring to the last index. So if you just think of m minus 1 as this last index number, it will help simplify the formula. And then I, in this case, is referring to the original I index. So let's take a look at 1. If we know that m minus 1 is the last index, which is 2, then we'll do 2 minus 0 equals 2. And sure enough, 1 moves to index 2 when it's a column. Now let's try number 9. We know m minus 1 is 2, minus 2 is going to be 0. And again, I is now 0 index when it becomes a column. Let's see that written out in the element positions. So as I just discussed, numbers 1, 2, and 3 all begin in index 0 for I. And when you apply this formula, m minus 1, so 3 rows minus 1 equals 2, minus 0 equals 2, that's where the new column index is derived from. Let's jump over to the final row, 7, 8, 9, to see that same pattern. 7, 8, 9 start in index 2. So when you do m minus 1, 3 rows minus 1 is 2, minus 2 equals 0. You'll see that they all flip to the new I index in the column of 0. Now that we've reviewed how the matrix elements move, let's think through the steps in our solution. Rotating a matrix by 90 degrees is going to involve 2 main operations. The first one will be transposing the matrix, which is when we're going to be converting rows into columns by swapping elements at ij with elements at ji. The next thing we want to do after transposing is reverse the elements in each row so that it will complete the clockwise rotation. Here's the pseudocode, and the main idea here is that we will loop over each row in the original matrix and place its elements into the corresponding columns in the rotating matrix. But we also need to reverse the order of the rows as we insert them into the columns. So the first step will be to get the number of rows and columns in the original matrix. We'll use those to define the loops below. Next, we'll convert the rows into columns, which is transposing the matrix. We'll have an outer loop that goes through each row. It's going to start at 0 and it's going to continue to be less than the row length. We'll have an inner loop, j, which is for the columns, and that's going to start at index I to ensure there's no overlap in the swapping, and it's going to continue up to less than the length of the columns. Next, we'll swap the values at matrix ij with the value at matrix ji. We then need to reverse each row in the matrix. I, from 0 up to less than the row length, we're going to reverse the elements of the matrix, and then we'll return the modified matrix after the rotation. Let's focus on this step where we are transposing the matrix. Transposing means that we're swapping the elements along the diagonal of the matrix, which is turning the rows into columns. So when we're talking about the diagonal, we're referring to the elements where the row at index I is equal to the column at index I. So for instance, we have row of 0, column of 0. That's the first element on our diagonal. Row of 1, column of 1 is 5. Row of 2, column of 2 is 9. So you look at this upper triangle, and that's what we will be doing the swaps on. So this upper triangle contains elements where I is always less than or equal to j. The reason we only want to loop through this upper triangle is that each swap already is going to affect two elements. For example, you might take something at element 0, 1, and you are going to swap that with element 0, 1. So 2 and 4 will already swap, which means if you access these elements down below the triangle, you'll be swapping them again and ending up in the original order of the matrix. Let's go through the swaps one by one. When you transpose a matrix, you're looking to switch the rows into columns. So we want to take elements at I, j, and switch them into j, I. Let's start with our first element, 1, that is in 0i, 0j. We want to switch that to 0j, 0i, so in this case, it remains in the same spot. The next element along this first row is going to be 2. 2 is in the position 0i, 1j. So now we want to swap that with 0j, 1i, and that's number 4. So you'll see over here, they are going to shift position. Next in this first row is the number 3, which is at 0i, 2j. We're now looking for 0j, 2i. We find the 7, and those are going to swap places over here. And this continues down, so now that we're done with row 0, we're now going to go to row 1, 1, because again, we're only sticking to this top triangle where j starts where I is. So we start at 1 for I, and j, it will start at 1 as well. When we swap that to a 1 by 1, it's going to stay in the same spot. That's the center of our matrix. Next, we'll move down this second row to number 6, which is at I of 1, j of 2. So we're going to now look for j of 1, I of 2. And those two will swap. And then the final element, number 9, is in the 2, 2 position. So when it swaps, it stays in the same spot. We have now transposed the rows into columns, but what you notice is they haven't rotated 90 degrees clockwise yet. So row 1 has become column 1, row 2 has become column 2, row 3 has become column 3, and we need to reverse the order of that with our code. Now that we understand the approach to our code, let's get started. First, we want to define our function. I'm going to call it rotate matrix clockwise and pass in a matrix. Next, I'm going to paste in the pseudocode that we reviewed. First, we want to define the number of rows and columns so that we can use those variables in our loops below. So we'll do const row length, and we'll define that as matrix dot length. Next, we'll create the variable column length, and we'll define that as matrix at 0 index dot length. Our next step is to transpose the matrix from rows to columns. So we're going to start with our outer loop here. We'll do a for loop. We'll use the variable I to define our rows. We'll start at 0, and we're going to go up to less than the row length and iterate incrementally. And I'm going to move this outer bracket down here, and we'll move on to our inner for loop. And this will be j to define our columns, and we're going to set j as equal to I so we can stay in that upper triangle without repeating elements. And we're going to do j is less than column length, And again, iterate incrementally. Next, we're going to use destructuring to swap the values from ij to ji. So we'll use our matrix at I, j, and j, I, and then we will swap the order of that on the right side. Next, we'll move on to step 2, which is reversing the order of each row. So we'll start with our for loop down here. We're going to do let I equals 0 again for our rows. Go up to less than row length. And iterate incrementally. Move my bracket down below. Then we need to reverse the elements. Move this up. So we'll take the matrix at I for our rows, and we're going to reverse those. And the last thing we need to do is return the matrix. And that's the end of our code. The last thing we want to do is just review the code, see if there's any errors that need to be corrected. Like I already noticed there's a curly brace out of place and an extra space here. So the easiest way to format that is just to format the document. And next we'll go through line by line. So on row 1, we're defining the function, calling it rotate matrix clockwise, and we're passing in a parameter called matrix. Next, we're initializing 2 variables for row length and column length to be used below. Then we're going to transpose the matrix from rows to columns. So we'll start our outer loop with I starting at 0. Next, we'll start our inner loop with J starting at I, so we don't have duplicates. And then we'll use destructuring to swap the values from ij to ji. And after converting rows into columns, we need to reverse the order of the rows so that they're in the clockwise formation. So now we're coming down to this for loop, iterating through the rows, and then reversing the elements of the matrix. After we have our rotated matrix, we return our matrix down below. Let's discuss the time complexity of the matrix rotation algorithm when we're dealing with a non-square matrix, where m represents the number of rows and n represents the number of columns. Our first step is transposing the matrix, and when we do that, we're looping through the matrix with 2 nested loops. The outer loop runs m times for the number of rows, and the inner loop runs n times for the number of columns. Since we visit each element in the matrix exactly once, this step has a time complexity of O to the m times n. Then our next step is reversing the elements in each row. Reversing a row is an O of n operation, and since there are m rows to reverse, this step also has a time complexity of O to the m times n. And when we break that down to the overall time complexity, both steps are going to contribute to the O of m times n. So the overall time complexity remains O to the m times n, which represents the number of elements that we process in the matrix. Now let's talk about why O of m times n doesn't simplify any further to, let's say, O n squared or O of n, even though we're used to seeing those types of complexities simplified in big O notation. So the reason it doesn't simplify is because big O notation reflects the input size. And in this case, the input size is a matrix with m rows and n columns. So both of these dimensions are contributing independently to the number of operations that we need to perform, which is why the time complexity depends on both m and n. There are some situations like this one with a matrix where the problem involves multiple independent inputs, and we have to keep both of those variables in to accurately describe the complexity. For instance, if in an m times n matrix, we collapsed that into a single variable, we'd be ignoring the fact that the number of rows, m, and the number of columns, n, can vary independently. Here are some examples of when we need to keep those two independent variables. O of m times n, in this case, it's really common with matrices or grids, where we have to include both rows and columns. O of m plus n might represent something like two sorted arrays where m and n represent the sizes of the two arrays. Or O of n times k could be used when processing n elements, each of which has k sub-elements, like in a nested data structure. So if you simplified O of m times n to n squared or n, you'd be assuming that m equals n, which might not be true. Both dimensions are important when describing the time complexity of this algorithm. So on a graph, even though we don't have something that explicitly says O of m times n, on the x-axis, we would be, so down here, we would plot the total number of elements in the matrix, which is m times n. And then on this y-axis for time, we'd be plotting the number of operations that the algorithm performs, which is also going to grow at m times n. So it will be linear, similar to the O times n. And as the total number of elements in the matrix increases, the time complexity will grow at the same rate. So today we walked through how to rotate a matrix by 90 degrees clockwise using two key steps: transposing the matrix, which is swapping rows and columns, and then reversing each row. So once everything's transposed, we reverse the elements in the row to complete the rotation. We saw that the time complexity of the algorithm is O of m times n, and this complexity reflects the fact that we need to process each element in the matrix exactly once, which scales linearly with the total number of elements. This approach is efficient, works for both square and rectangular matrices, and ensures that the matrix is rotated in place without requiring extra memory of us having to open a new array to hold the elements. Thanks for watching. I hope this helps you better understand matrices.